In this video, we will continue practicing integration by parts. This time around, I will show you how to use integration by parts to solve basic differential equations and evaluate definite integrals. I will also show you a shortcut called the table method. If you haven't watched the introductory lesson yet, you should definitely watch that first. This will make a lot more sense if you do. You can either click the link that appears in the upper right hand corner or find the link in the description. This is a BC only topic. Number 32 is a basic differential equation. To turn y prime into regular y, we need to integrate both sides of the equation. So now we have this. Unfortunately, we do not know a memorized rule for the antiderivative of arctangent u. And in order to use integration by parts, we really need a product, not a single factor. We can look at this as 1 times arctangent x over 2 dx, which will allow us to do integration by parts. The first step is to decide which part of this expression will be u and which part will be dv. To choose the best u, we use the acronym LIATE, which ranks the various types of expressions in order from the best u to the worst u. The number 1 is the most basic algebraic factor, and of course arctangent is an inverse trig factor. Inverse trig is a better u than algebraic, so let's let u equal arctangent x over 2. That means dv must equal 1 dx. Next, we need to take the derivative of both sides of this equation, but remember that the derivative of arctangent u is 1 over u squared plus 1 times u prime because of the chain rule. In this case, the inside part is x over 2, so we have 1 over x over 2 squared plus 1 times the derivative of the inside part. This is like 1/2 x, so the derivative will be 1/2. X over 2 squared is the same as x squared over 4. I need to get rid of the fraction in the denominator, so I'm going to multiply by 4 over 4. The idea is that this 4 is going to distribute across the binomial, and the 4 will cancel out this 4, and I will end up with x squared plus 4. So now we have this. On the next step, this 2 will divide into the 4 and leave a 2. Also, for integration by parts, we really want du by itself. So multiplying both sides by dx will move the dx over here. And integrating both sides of this equation, we get v equals x. The answer comes from setting up the right-hand side of the integration by parts formula, starting with u times v, which is this times this. Then we have minus the integral of v du, which is this times this. So now we have this. We can find this integral by U substitution if we let u equal x squared plus 4, which means u prime will equal 2x. Doing the substitution gives us this, but instead of dx, we write du over u prime. In other words, du over 2x. But then we notice that the 2x and the other 2x cancel out. So now we have this. The antiderivative of 1 over u is the natural log of the absolute value of u, which is x squared plus 4 plus c. This is the final answer. Notice that we do not need the absolute value symbols because x squared plus 4 is always positive. If we were to solve this problem by the normal method, we would have to do integration by parts twice. However, I'm going to teach you a shortcut that will allow us to integrate problems like this very quickly. It's called the table method. It starts off the same. We still have to choose the best u. We have an algebraic factor times an exponential factor. algebraic is better than exponential for u. So let's let u equal x squared. That means dv will equal e to the negative 2x dx. The table method only works when u will eventually become 0 with repeated differentiation. So we can start by taking the derivative of x squared over and over until it becomes 0. The derivative of x squared is 2x, and then the derivative of 2x is 2, and the derivative of 2 is 0. So this shows that the table method will work. Now we take the antiderivative of the dv expression over and over again until we get down to the 0 row. We have to do a mental U substitution here. U is negative 2x, so U prime is negative 2. We divide by U prime by putting a negative 1/2 in the front. Then the antiderivative of e to the u is e to the u. On the next row, we bring down the negative 1/2 that is already there in the front, but we have to multiply by another negative 1/2 because of the u substitution. And then the antiderivative of e to the u is e to the u. That's 1/4 e to the negative 2x. For the last integral, we bring down the 1/4 that we already have. And again, we multiply by negative 1/2 for the mental u sub. And the antiderivative of e to the negative 2x is e to the negative 2x. The antiderivative of the original problem will have 3 terms which will come from the products of each of these diagonals, with one exception. This pattern determines what the sign of each term will be. For the first product, we will keep the sign that we get. For the second product, we will change the sign. And for the third product, we will keep the sign that we get. So the first term will be x squared times negative 1/2 e to the negative 2x. And we keep the sign that we have. The second term will come from 2x times 1/4 e to the negative 2x. This would be 1/2 x e to the negative 2x, but we change the sign and make it minus. The last term will come from 2 times negative 1/8 e to the negative 2x. That gives us negative 1/4 e to the negative 2x. And we keep that sign. Instead of writing keep, change, I usually put plus, minus, plus, minus. It's easier. This is a definite integral which we must evaluate from 0 to 2. So we need to find the value at 2 minus the value at 0. Here's the value at 2. Now we have to subtract the value at 0. Notice that both of these terms have an x in them. So if we plug in 0, they will go away. If we put in 0 for this last x, we have e to the 0 power, which is 1. So we will be left with negative 1/4. Minus a negative is a positive. So this is one version of the final answer. The first 3 terms are like terms, so we can simplify this a little bit. Making like denominators gives us this, and combining like terms gives us this or this. For number 44, we have an algebraic factor times an inverse trig factor. As we choose the best u, we consider that inverse trig is better for u than algebraic. So let's let u equal arcsine x squared, which means that dv must equal x dx. Remember that the derivative of arcsine u is 1 over the square root of 1 minus u squared, but then, because of the chain rule, we have to multiply by u prime. So du will equal 1 over the square root of 1 minus x squared squared. then we need to multiply by the derivative of this inner function, which is 2x. I'm going to put the 2x in the top, and don't forget the dx on the end. Taking the antiderivative of both sides, we get v is equal to 1/2 x squared. Let's rewrite this as x to the 4th power. Now it's time to set up the integration by parts formula, starting with u times v. So that's this times this. Then we have minus the integral of v du, which is this times this. These 2's are going to cancel out, and we will have x to the 3rd power in the numerator. We can find this integral using U substitution. However, we are already using the variable u, so let's call it t substitution, and let's let t equal 1 minus x to the 4th power. That means that t prime is going to equal -4 x to the 3rd power. Doing the substitution gives us this, but instead of writing dx, we write dt over t prime, or dt over -4 x to the 3rd power. Then we notice that the x to the 3rd power cancels out. On the next step, the -4 will come out in the front as a positive 1/4. So now we have this. For the antiderivative of t to the -1/2 power, we add 1 to this exponent, which gives us t to the positive 1/2 power. Then we divide by the new exponent, which is the same as multiplying by 2. 1/4 times 2 simplifies to 1/2. And replacing t with 1 minus x to the 4th power gives us this. This is a definite integral, so instead of putting a plus c, we apply the limits of integration from 0 to 1. So we need to find the value at 1 minus the value at 0. When we put 1 in for x squared, it's just a 1, so we don't have to write anything. Arcsine of x squared becomes arcsine of 1, and we ask ourselves the sine of what angle is equal to 1, and that is pi over 2. So there you go. Then we have plus 1/2 the square root of 1 minus 1 to the 4th power. 1 to the 4th power is 1, so this is really 1 minus 1, which is 0. So this term is gone. So this is the value at 1. Now we just have to subtract the value at 0. Because of the x squared, if you put a 0 in, this whole term is gone. So that leaves us with 1/2 times the square root of 1 minus 0, which is the square root of 1, which is 1. So this is the value at 0. So this is the final answer. For number 48, as we try to choose the best u, we notice that we have an algebraic factor and a trigonometric factor. Algebraic is a little bit better than trigonometric for u. So let's let u equal x. That means dv is equal to secant squared 2x dx. Taking the derivative of both sides, we have du is equal to dx. Remember that the derivative of tangent is secant squared. So the integral of secant squared is tangent. Taking the integral of both sides, we have v equals. Here we have to do a little bit of u substitution. U is 2x, so u prime is 2. We always have to divide by u prime, which we show by putting a 1/2 in the front. And the antiderivative of secant squared is tangent. So we have tangent of 2x. Now it's time to set up the integration by parts formula, starting with u times v. So that's this times this. Then we have minus the integral of v du, which is this times this. So now we have this. We have a memorized rule for the antiderivative of tangent x dx. It's negative natural log absolute value of cosine x plus c. Because we have tangent of 2x, we have to do the mental U substitution. U is 2x, so U prime is 2. We always divide by U prime, which we show with a 1/2 in the front. That's in addition to the 1/2 that was already there. Now here comes the memorized rule. The negative in the front is going to cause this negative to become a plus. But then we have the natural log of the absolute value of cosine 2x plus c. Actually, we won't do plus c because this is a definite integral. But first, 1/2 times 1/2 is 1/4. Next, we apply the limits of integration from 0 to pi over 8. So we need to find the value at pi over 8 minus the value at 0. So here is the value at pi over 8 minus the value at 0. The value at pi over 8 simplifies to this, and the value at 0 simplifies to 0 because the cosine of 0 is 1, and the natural log of 1 is 0. The tangent of pi over 4 is 1, so we don't write anything, and the cosine of pi over 4 is radical 2 over 2. So this is the final answer.